NEC Table 450.3 addresses the overcurrent protection of transformers. Note 2 specifically states that fuses installed on the secondary side of a transformer shall be located as near as practicable to the transformer. The key phrase here is as near as practicable. This isn't just a suggestion, it's a requirement with safety and operational efficiency in mind. The intent is to ensure that the overcurrent protection devices, in this case fuses, are readily accessible for inspection, maintenance, and replacement. Consider the implications of having these fuses located remotely. Firstly, in the event of a fault or overload condition that causes a fuse to blow, time is of the essence. Locating the fuses far from the transformer adds a necessary delay in identifying and correcting the problem. This delay could potentially lead to further equipment damage, extended downtime, and increased safety risks. Secondly, accessibility is crucial for routine maintenance and testing. Electrical systems need periodic inspections to ensure they are operating safely and efficiently. Having fuses located in separate, distant locations makes these inspections more time-consuming and difficult. This can increase the likelihood of overlooking potential problems or delaying necessary repairs. Thirdly, consider the scenario of an emergency. If a fire or other hazardous condition arises, the ability to quickly de-energize the transformer is paramount. Having fuses located remotely can hinder this process and potentially put personnel at risk. The NEC doesn't provide a specific distance that defines as near as practicable. This is because the ideal location will depend on various factors, such as the size and type of transformer, the layout of the building, and the specific electrical system design. However, the general rule of thumb is to locate the fuses as close as possible to the transformer while still ensuring they are accessible and protected from physical damage. In situations where it's not feasible to locate the fuses directly adjacent to the transformer, consider the following factors. Firstly, minimizing the distance. The shorter the distance between the transformer and the fuses, the better. Aim to keep the distance to a minimum, ideally within the same electrical room or enclosure. Secondly, ensuring accessibility. The fuses should be easily accessible for inspection, maintenance, and replacement. Avoid locations that are difficult to reach or require specialized equipment to access. Thirdly, providing clear labeling. Clearly label the fuses to identify the transformer they protect and the circuits they serve. This will help ensure that the correct fuses are replaced in the event of a failure. Fourthly, considering environmental conditions. Protect the fuses from environmental factors such as moisture, dust, and extreme temperatures. These factors can degrade the performance of the fuses and increase the risk of failure. Fifthly, consulting with a qualified electrical engineer. If you're unsure about the best location for your transformer secondary fuses, consult with a qualified electrical engineer. They can help you assess the specific requirements of your installation and ensure that it complies with the NEC and other applicable codes and standards. In your described situation, having the fuses located 150 feet away in two separate mechanical rooms servicing distinct areas of a building is a clear violation of NEC Table 450.3a. This distance is excessive and would make it difficult to access and replace the fuses in a timely manner. This is especially true since you mentioned the areas are for different functions, implying that there may not be an electrical relationship between the two areas other than the transformer itself. Therefore, it's imperative to relocate the fuses to a single location that is as near as practicable to the transformer. This will not only ensure compliance with the NEC but also improve the safety and reliability of your electrical system. It is beneficial to discuss some of the specific reasons why these requirements are in place. Electrical codes are designed to provide for safety and minimize the risk of electrical shock, electrocution, and fire. Transformers, while reliable pieces of equipment, are not immune to failure. When transformers fail, they can do so catastrophically, leading to large overcurrent situations. Without proper overcurrent protection, these faults can lead to electrical fires and equipment damage. The fuses are intended to interrupt the flow of electricity in these situations, preventing further damage and ensuring the safety of personnel and property. The closer the fuses are to the transformer, the faster they can react to a fault, minimizing the amount of energy released into the system. A longer run of unprotected conductors between the transformer and the overcurrent device creates a greater opportunity for a fault to occur and propagate. The requirement for fuses to be as near as practicable also addresses the issue of coordination. Coordination refers to the selective tripping of overcurrent devices. The goal is to ensure that only the overcurrent device closest to the fault trips, minimizing the impact on the rest of the electrical system. When fuses are located far from the transformer, it can be more difficult to achieve proper coordination. This can lead to nuisance tripping of upstream overcurrent devices, causing unnecessary downtime and disruption. The NEC isn't merely a set of arbitrary rules, it's a collection of best practices developed over many years based on real-world experience and engineering principles. These requirements are in place for a reason, and it's important to understand the underlying rationale behind them. Ignoring these requirements can have serious consequences, not only in terms of code violations but also in terms of safety and reliability. Regarding older facilities and installations, it's possible that some existing installations may not fully comply with the current NEC requirements. This could be due to changes in the code over time, or it could be due to original installations that were not up to code. However, the fact that something may have been done in the past doesn't make it acceptable today. The NEC is constantly evolving to incorporate new technologies, improve safety practices, and address emerging hazards. It's important to stay up to date with the latest code requirements and to ensure that your electrical system is compliant. When renovating or modifying an existing electrical system, it's generally required to bring the entire system up to the current code. This may involve relocating fuses, upgrading wiring, or installing new equipment. The specific requirements will depend on the scope of the renovation and the local codes and regulations. In summary, the placement of transformer secondary fuses is a critical aspect of electrical system design and must comply with NEC Table 450.3a. Locating fuses as near as practicable to the transformer is essential for safety, reliability, and code compliance. Failure to comply with these requirements can have serious consequences and should be avoided at all costs. It would be useful to discuss how this relates to other parts of the NEC. The NEC provides specific guidelines for transformer overcurrent protection. Article 450 covers transformers generally, and Article 240 addresses overcurrent protection. These articles work together to ensure that transformers are protected against overloads and faults. Specifically, NEC Section 450.3a and b provide the requirements for transformer overcurrent protection based on the transformer's voltage and current ratings. These sections specify the maximum allowable size of the overcurrent devices, such as fuses or circuit breakers, based on the transformer's nameplate ratings. It's important to carefully review these sections and consult with a qualified electrical engineer to ensure that your transformer overcurrent protection is properly sized and coordinated. Moreover, it's not only the location of the fuses that matters, it's also the type and rating of the fuses. The fuses must be properly sized to protect the transformer from overloads and faults, while also allowing for normal operating conditions. Using undersized fuses can lead to nuisance tripping, while using oversized fuses can compromise the protection of the transformer. The NEC provides specific guidelines for selecting the appropriate fuse size based on the transformer's nameplate ratings and the type of load it serves. These guidelines take into account factors such as the transformer's impedance, the inrush current of the load, and the ambient temperature. It's important to carefully consider these factors when selecting fuses to ensure that they provide adequate protection without causing nuisance tripping. In addition to fuses, circuit breakers can also be used for transformer overcurrent protection. Circuit breakers offer some advantages over fuses, such as the ability to be reset after a trip and the ability to provide adjustable trip settings. However, circuit breakers also have some disadvantages, such as a higher cost and a more complex design. The choice between fuses and circuit breakers will depend on the specific application and the preferences of the electrical engineer. Regardless of whether fuses or circuit breakers are used, it's important to ensure that they are properly coordinated with other overcurrent devices in the electrical system. Coordination is the process of selecting overcurrent devices so that only the device closest to the fault trips, minimizing the impact on the rest of the system. This can be achieved through the use of time current curves, which show the tripping characteristics of different overcurrent devices. By carefully analyzing these curves, electrical engineers can select devices that will coordinate properly and provide selective tripping. Another important consideration when designing transformer overcurrent protection is the type of load that the transformer serves. Different types of loads have different characteristics and require different types of overcurrent protection. For example, motor loads typically have a high inrush current when they start, which can cause nuisance tripping of overcurrent devices. To address this issue, special types of fuses and circuit breakers are available that are designed to withstand the high inrush current of motor loads. These devices typically have a time delay characteristic that allows them to ride through the inrush current without tripping. Similarly, lighting loads may require special types of overcurrent protection to address issues such as harmonic currents and voltage surges. Harmonic currents can cause overheating of transformers and other electrical equipment, while voltage surges can damage sensitive electronic equipment. To address these issues, special types of fuses and circuit breakers are available that are designed to mitigate the effects of harmonic currents and voltage surges. The NEC also requires that transformers be protected against overload conditions. Overload conditions occur when the transformer is subjected to a current that is higher than its rated current for an extended period of time. Overload conditions can cause the transformer to overheat and eventually fail. To protect against overload conditions, the NEC requires that transformers be equipped with overload protection devices, such as thermal overload relays or current transformers with overcurrent relays. These devices monitor the transformer's current and trip the overcurrent device if the current exceeds a predetermined level for a specified period of time. The NEC also provides specific requirements for the installation and maintenance of transformer overcurrent protection devices. These requirements cover topics such as the location of the devices, the type of enclosure required, the method of wiring, and the frequency of testing. It's important to carefully follow these requirements to ensure that the overcurrent protection devices are properly installed and maintained and that they will function reliably in the event of a fault or overload. One final point to consider is the importance of documentation. It's essential to maintain accurate documentation of all transformer overcurrent protection devices, including their type, rating, location, and settings. This documentation should be readily available to electrical personnel for inspection, maintenance, and troubleshooting purposes. The documentation should also include a single-line diagram of the electrical system, which shows the location of all overcurrent devices and their relationship to other electrical equipment. Maintaining accurate documentation can help to ensure that the electrical system is properly maintained and that it will operate safely and reliably. In conclusion, transformer overcurrent protection is a complex topic that requires careful consideration of many factors. By following the guidelines in the NEC and consulting with a qualified electrical engineer, you can ensure that your transformer is properly protected against overloads and faults and that your electrical system is safe and reliable. And again, the location of the secondary fuses is a crucial component in ensuring the overcurrent protection scheme works as designed.